Hello and welcome to the 12th tutorial in this mini-series, although it's not quite such a mini-series anymore, on calculus at the higher level. And in the last two tutorials we talked about finding stationary points of functions, and in this and the next two tutorials I will talk about an application of finding stationary points which is called optimisation, and it's probably one of the major tools, major applications of calculus as a tool used in science and mathematics. And it will be used when you have a problem or a system where you want to find an optimal solution given some constraint. Now, in this tutorial I'm going to show you a very simple example followed by going through an actual higher mathematics exam problem. But actually in the next two tutorials I want to show you two slightly more advanced examples. They're not things that you would find in the exam, so they'll be optional tutorials, but I think they're worth seeing because you'll really get an understanding of why optimization is such an important application of calculus. So let's start with this very simple example. We want to think of a problem where we need to optimize something given a constraint. And what I'm going to set this up as is the following. Imagine we have a length of rope, length L, and we want to make rectangle with that rope. So here is a rectangle made from the piece of rope. You can imagine laying out this piece of rope on the ground in the garden or something, or in the park, and you're making a rectangle, and there are the two ends of the rope meeting there. And the question is, what shape should the rectangle have to maximize the area inside? So let's call A the area of the rectangle, and the perimeter of course will just be given by L, the length of the rope. So let's call these sides of the rectangle X, and then because the total perimeter is L, the sum of these two sides must be L take away 2x. So each of these sides will be L over 2 take away x. And so we can just quickly check then that the total perimeter here is x plus this, which is L over 2, plus x plus this, and we just get L over 2 plus L over 2 is L, so that's fine. And we can see that the area contained by the rope in the rectangle is a function of x. And in fact will just be given by the length times the breadth. So the area will be x multiplied by L over 2 minus x, which in fact is a parabola. And in fact, well, I won't sketch that, but you can see that that's just a parabola that vanishes when x is 0, and it also vanishes when x is L over 2. Obviously, if I take this side to go to 0, I just have sort of a hairpin made out of the rope and it has no area enclosed. Alternatively, if I take x to be L over 2, this side vanishes and again I have a hairpin with no enclosed area. So there'll be some intermediate value of x where the area is maximized. Now, of course, we could figure this out just from geometry or by looking at this function, but let's use the method of stationary points to solve this problem, and that will give us then the idea of how to use it in more complicated examples where in fact calculus will be the only approach that you can really use. So A is a function of x, and we want to find that value of x where there is a stationary point, and that means we want to differentiate this function. So let's just multiply out the bracket so that we can see what we're dealing with here. We have x times L divided by 2 take away x squared, and I now want to differentiate the area with respect to x. So I get the derivative now. If I differentiate the first term, it's just a constant times x, so the derivative will just be that constant. Differentiate the second term, the derivative of x squared is 2x. So this is my derivative, and I want to set this equal to 0 for the stationary point. And so solving this simple equation here then, I have that 2x at the stationary point is equal to L over 2, and so dividing both sides by 2, I have that x is equal to L divided by 4. So if this side is L divided by 4, I can see what the other side is. The side at right angles, which has a length L over 2 take away x, will have a length of L over 2 take away L over 4, which of course is also L over 4. So we have this lovely result here that the optimal shape is actually a square. Which is a very cute result, and in fact you often see this in maths and science, that when you're solving optimization problems, it's often the case that the optimal solution in some sense has the greatest symmetry, and we can actually see why this result must be true without doing any maths at all. Actually, simply by logical argument, we could say that the shape with the optimal area should not depend on the orientation in which we draw this. So as we change x from a small value to a larger value, we go from a rectangle that's skinny in this direction to a rectangle that's skinny in this direction. But the area itself can't care for its optimal value on that orientation. Therefore, the optimal area has to be such that all sides are equal. It doesn't care about whether you have tall and skinny or long and skinny, and so the only solution that doesn't care about that is a square, which has a symmetry and doesn't care about which orientation you draw the rectangle. Now, this is obviously the solution that's a maximum for the area. Remember, when you're solving stationary point problems, you do need to show whether you have a maximum or a minimum. It could even be an inflection point. I won't do that here because it's such an obvious example, but what I'll do now is turn to an exam problem, and we will see then a similar kind of problem that we can solve. And to get full marks, you will have to go that final mile, as it were, and show what kind of stationary point you have. So hopefully I can actually change the screen here in the right direction. No, I did it in the wrong direction, but never mind. Here is the problem on the screen here. This is, I think, from 2016 on the second part of the exam, question 7. And we'll just have a look here at what they're asking us. A council is setting aside an area of land to create 6 fenced plots where local residents can grow their own food. Sounds like a sort of a feudal state. Each plot will be a rectangle measuring x by y as shown in the diagram. So this is looking ahead of COVID, when the grocery stores are empty and we're just all keeping plots of land and growing our potatoes and turnips. Right, now the area of land being set aside is 108 square meters. So that's the constraint, and you see how these optimization problems nearly always involve a constraint. It says show that the total length of fencing L is given by, so first of all we have to just derive an expression for the total length of fencing, and then the optimization part of the problem in part B, it says find the value of x that minimizes the length of fencing required. So while I'll let you just study that for a second, I will quickly make a sketch so that when we go back to the paper it will all be ready. So it's 2016, paper 2, question 7, and we have this particular shape which I will quickly draw. So it's an area of land divided into 6 equal rectangular plots, and the horizontal distance for each plot is x, and the vertical distance for each plot is y, and the total area is 108 square meters. Right, okay, and we have to derive a particular formula there. So, going back then to this screen, and of course I went the wrong way again because that is just the way things are. Here's a sketch of that problem, and we have to first of all derive an expression for the total length of fencing, in other words the total length of these red lines that I've drawn. So let's see, the length of the fencing is equal to, well, we have these horizontal lengths are x, and we have 1, 2, 3, 4, 5, 6, 7, 8, 9 lots of x, and the vertical lengths are y, and we have 1, 2, 3, 4, 5, 6, 7, 8 lots of y. And now what we need to do is eliminate y by using the constraint, and the constraint here is that the total area is 108, but you can see that I have 6 of these plots, and each plot has an area of x times y, so that is an expression for the total area, and that's equal to 108. So therefore I can just now solve this equation for y by dividing both sides by 6x. So I have that y is 108 divided by 6x, which I can simplify. Dividing 6 into 108, I have, let's see, finding this harder than I should. 6's into 10 go 1, and 6's into 48 go 8. So that is 18 over x. And so now then, just putting y equals 18 over x into this formula, we have that the total length, let's just call that L of x, is 9x plus 8 lots of y. So it's 8 times 18 divided by x, and we can just tidy that up. 8 lots of 18 are 144, and I recall that indeed was the formula we were asked to derive for the first part of the question. So that's how these questions typically go on the Scottish Maths Higher. The first part is deriving the function that you will then be optimizing, incorporating the constraint. And now comes the calculation part. We want to find the value of x which minimizes, now we want to minimize the total amount of fencing, presumably but the fencing is very expensive and we need to make it as cost effective as possible. So let's differentiate this function, and to get this function into a form that allows us to differentiate it, you following the kind of the rules that we know, we just want to write that second term of 144 over x as 144 x to the minus 1, and then we remember that when we differentiate x to the minus 1 we bring down the power and then have x to that same power with 1 less, and so the derivative of x to the minus 1 will be minus x to the minus 2. So differentiating this, then we have dl by dx is 9, the derivative of 9x is 9, and then we have minus 144 x to the minus 2. And let me just write that in a nicer way. taking that x to the minus 2 and writing it as 1 over x squared. This is the derivative, and we want to set this equal to 0 for the stationary point. So let's now solve this equation for x. So we want to solve the equation that 9 is equal to 144 over x squared, and multiplying through both sides by x squared, we have that 9x squared is 144. Then dividing by 9, I have that x squared is 144 divided by 9, which of course I can recognize is 12 squared divided by 3 squared, and this means then that x will be equal to 12 divided by 3, which is equal to 4. So that's fine. The value of x which optimizes this function is x equals 4, and in that case we can work out what the length of fencing would be in total. Let's see, we would have that L of 4 is 9 times 4 plus 144 divided by 4, which is 36, and then 144 divided by 4 is also 36. And that's interesting. You see, I mentioned about how symmetry is often revealed when you optimize something, and here what we found is that the optimal solution here has that the total amount of fencing in the horizontal direction is actually equal to the total amount of fencing in the vertical direction. And so the total length then of fencing, the minimum length, is 72 meters. Now, as a final step here, let's just do an exercise to show that indeed this solution, this value of x, minimizes the length of fencing. So what we'll do is take a value of x a little bit less than 4 and another value of x a little bit greater than 4, plug it into this formula for the derivative and look at the sign of the derivative. So if I choose x equal to 3, for example, to be on the left side of this solution, then the derivative L primed is given by 9 take away 144 divided by 3 squared, which is 9. And it's very clear that 144 divided by 9 is greater than 9, and so this will be a negative number. And then if I go to the right side of x equals 4, if I take x equals 5, I have that L primed is 9 minus 144 over x squared. 5 squared is 25. And then it's clear that this number here is less than 9, and so 9 minus this will be positive. Notice that I'm not worrying about evaluating these numbers because all we care about is the sign. It may be that an examiner would want you to write the particular value down, so you may as well do that using a calculator, but just for the purposes of this tutorial we just care about the sign of these derivatives. So we can make a little table. We can compare values of x and their corresponding signs of the derivative, and what we showed was that when x is 3, 4 and 5 respectively, we have the derivative is negative, is 0 at x equals 4 because that's the stationary point, and then is positive at x equals 5. And the nice way to visualize that then is just to say, right, we had a negative derivative here, a 0 derivative here, and a positive derivative here, and we can see then that this is indeed a minimum as was required by the question. As I mentioned in the previous tutorial on stationary points, if you study calculus at a slightly more advanced level, you wouldn't really use this rather, cumbersome technique to find the type of stationary point. You would do what's called taking the second derivative, and the sign of the second derivative immediately tells you whether you have a maximum or a minimum or a turning or a inflection point. But in the higher math syllabus, you don't meet the second derivative, and so you rely on this method, which is perfectly fine if you use it sensibly to find the nature of the stationary point. So I'll stop there. That's showing you two examples of optimization. A simple example, which I think is very beautiful because it's so simple and the answer itself is very neat, that the type of rectangle that maximizes its area for a given perimeter is a square. Very symmetrical answer. And then we just solved, using stationary point method, a problem from the Scottish Higher Maths paper 2016, paper 2, question 7. I won't go through the scenario, but essentially we were asked to derive a particular function and minimize it, which is what we've done here. So I hope that's been helpful. I would encourage you to watch the next two tutorials, even though they go a little bit beyond the kind of optimization you see at Higher, but I think you'll get quite an interesting idea from those about why you're studying optimization and how powerful indeed it can be as a mathematical tool in science. So with that, thank you very much for your attention, and I'll see you next time.